comments to two slides. Lecture 3 BSU. So here we can see a different situation. If the anchor is not small enough, we cannot neglect the buoyant force acting on it. So the free body diagram for the anchor now should show four forces. The force of tension, which we have found, the force of gravity, the normal force, and the buoyant force. And the word critical still means the normal force becomes equal to 0. However, when the normal force is 0, we have now two forces pointing up and one force pointing down. And to balance forces out, we should say that the magnitude of the tension plus the magnitude of the buoyant force together should cancel gravity, so should be equal to the magnitude of the force of gravity. And now, if we need to calculate that critical mass, that's what we have to calculate. So that 3 newtons, and to get the buoyant force we have to calculate it, and it's equal to density of water times G times the total volume of the anchor. So if the anchor is a cube 5 centimeter by 5 centimeters by 5 centimeters, so in that case we have to calculate this product. 5 centimeters converted in meters cubed, and the whole thing divided by 10 again. So that's going to be in kilograms. And that's another slide. When an object is attached to a spring scale and the object is in vacuum or in air, the reading is equal to the tension, which is equal to the force of gravity acting on this object. So that's how we weigh things. This is mg, this is tension, and we read this number here. So if the mass of the ball is 500 grams, which is a half of a kilogram, to calculate this reading, all we have to do is just multiply, well, a half of a kilogram times about 10, 5 newtons. Now, 750 grams, that's how much water we have in the beaker. So this reading should be equal to, well, converting grams and kilograms, 0.75 times 10, 7.5 newtons. The difference here is due to buoyant force acting from water on the ball. That changes the reading in the spring scale. So the new reading will be less by the amount of the buoyant force acting on the ball. However, by the Newton's third law, there is a force acting from the ball on the water, and that force has the same magnitude but opposite direction to the buoyant force. That changes the reading of this scale by the same amount but in opposite direction. So all we have to just calculate the buoyant force, and then we should subtract it here or add it there. And to calculate the buoyant force, we have to do again this density of water times G times the volume. Well, the volume below the surface, well, in this situation the whole ball is in water, So this should be the total volume of that ball. So in numbers 1000, 10, and the volume of a sphere 4/3 times pi times the radius cubed. First of all, this is the diameter. So to get the radius, we have to divide diameter by 2. And secondly, that's in centimeters. And we want to use the International System of Units. So 5 centimeters is 0.05 of a meter. When we finish this calculation, that will give us newtons.